Write your name and your seat number in the chat box. So yesterday we completed, this is the chemical reactivity oxidation state of group 16, group 17 and group 18 elements, then reaction with halogens, reaction with hydrogen, reaction with halogens we are discussing. But just I want to again remind you one thing for the board examination. This is very important. This is reactions of group 17 elements with halogen. They forms hydrogen halide. For the board examination, this question is asked, which is a weak acid and which is a strong acid. Remember, acidity always depends upon the compound from where the hydrogen is easily removed. So if the bond is very strong, the hydrogen is not easily removed, but the bond between this hydrogen and iodine, this bond is very weak. So this is strong acid, and the bond between this hydrogen and fluorine is very strong bond. So hydrogen requires more energy to break this bond. So this is a weak acid and this is strong acid, remember. So this question is asked for board exam, why this is a HF is a weak acid and why HI is a strong acid. And another one question is asked for the examination is thermal stability. HF is thermally more stable than the HI because of the bond dissociation energy, means the amount of energy required to break the bond between hydrogen and fluorine is very high energy is required. We can see here in this table 574 kilojoule per mole. It is the amount of energy required to break this bond. So that's why this HF is thermally more stable and HI is thermally less stable. And so today we will start the next part. Yes, this reaction of group 17 elements with halogens. So this yesterday we discussed about this reactivity towards halogens of group 16. Group 16, that is old style type oxygen, sulfur, selenium, tellurium, they reacts with halogens to form these types of halides. The hexahalides, then tetrahalides, and then dihalides. So hexahalides are this sulfur hexafluoride, selenium hexafluoride, then tellurium hexafluoride. They are formed by the direct combination of this sulfur and fluoride. These are the colorless gases. They are having this hybridization. This is a hybridization of this sulfur sp3d2 hybridization. That's why these are octahedral. When sp3d2 hybridization is there, they are having the octahedral structure. And the stability of halides, fluorides are more stable and the iodides are very less stable. Then I am coming to the tetrahalides, which kind of tetrahalides are formed. If the tetrahalides, the geometry is always remember trigonal bipyramidal. When the geometry when the hybridization is sp3d2, the geometry is octahedral, and when it is sp3 hybridization, remember sp3 hybridization is there, the shape is trigonal bipyramidal. Then I am coming to the dihalides, SCl2, ACCl2, TeCl2. These are the dihalides formed with group number 16 elements. They also having the sp3 hybridization and possess the tetrahedral structure. So these tetrahalides and dihalides having the sp3 hybridization, means this is a hybridization of this sulfur, selenium, tellurium, TeF4 and TeCl4. So Hexahalides, tetrahalides, dihalides are formed, and monohalides, these are dimeric in nature, S2F2, S2Cl2, AcCl2. So go through it. Till now, no any question is asked on this part, reactivity towards halogen. But don't neglect it, read it carefully. Then I'm coming to this part. So this is the reaction of halogens with halogens. It is called as when halogens combine with another halogens, they form a large number of compounds. It is called as interhalogen compounds, remember. So what is this interhalogen compounds in which X, X dash, both are halogens. X, X dash 3, X, X dash 5, and X, X dash 7. These are the types of interhalogen compounds. Interhalogen compounds means halogens combine with another halogens, they form such type of compounds where this X is a halogen which is having a larger size, and X dash is a halogen which is having smaller size. Same for this X, X dash 3, X, X dash 5, and X, X dash 7. This all we will discuss later because a separate section is there, interhalogen compounds. In that part we will discuss in this detailed. Now I am coming to the group 18 elements, the reaction of group 18 element, that is noble gases. Already they are chemically inert because they do not having tendency to lose electron or gain electron because their outermost shell is completed. But there are two noble gases, one is krypton and another one is xenon. Krypton and xenon, they can react with fluorine to form the fluoride. So one reaction is given here. Xenon in gaseous state reacts with fluorine and it forms a compound. It is XeF2. XeF2, this is one example is given. So like this XeF2, it can form XeF4, tetrafluorides, and then difluorides, xenon difluoride, xenon hexafluoride. So these are the compounds formed by xenon with halogens, remember. Now, next part is reactivity towards metals. First, we will discuss the reactivity of metals of group 16 elements. Group 16 elements, oxygens. Oxygen family, it reacts with metals. Some examples are given here. So, elements of group 16 reacts with metals to form these compounds. So, this is a reaction with aluminium metal. So 3O2 plus 4Al, they gives twice Al through O3, it is aluminium oxide is formed. And then sulfur reacts with copper, it forms copper sulfide. So this is the reaction with metals, remember. These are the group 16 elements, oxygen, sulfur, selenium, and these are the metals, aluminium, copper, and Mg. This selenium reacts with Mg, it forms magnesium selenide, MgSe. So these are some examples are given. So for the board examination, for 1 mark, any one reaction can be asked. Then group 17 elements, reaction of group 17 elements with metals, they react with metals to form metal halides, remember. So this is a Cl2 plus twice Ne, you know, this is a very famous twice NaCl. It is a common salt. Br2 reacts with Mg. It is MgBr2, magnesium bromide. It can react with Cl2 to give magnesium chloride. So the ionic character of these halides decreases in the order. So this metal and fluorides is more ionic, and metal and iodine, this is less ionic in nature. So metal fluorides, these are more ionic than the metal iodides. And see, I will explain these examples: SnCl4, PbCl4, SbCl6. These are also the metal halides. Reaction with tin, reaction with lead, reaction with antimony, reaction with uranium. So these are the metal halides having the metals in their higher oxidation state. This one, SnCl4, PbCl4, SbCl5, and UF6. In this, the Tin, Pb, Sb, and uranium, these are in the higher oxidation state. So these compounds are more covalent than this one, SnCl2, PbCl2, SbCl3, and UF4, because in this the metals having the higher oxidation state are more covalent. Remember, when the metals having the higher oxidation state, these are more covalent. These compounds are more covalent than these compounds, because in these compounds metals having the higher oxidation states. Then group 18 elements do not react with directly metals. So the reactivity towards metal is completed, and the reactivity towards halogen is also completed. So make a practice at your home which is more ionic and which is less ionic. Fluorides are more ionic, remember, because for the MCQ purpose this can be asked. Then I am coming to the allotropy. You are familiar with this word allotropy in 11th standard also, in the chapter number I think chapter number is group 1, no, group 13, group 14 and group 15 elements. In this chapter we already learn about the allotropy of carbon, diamond, graphite. These are the allotropes of carbon. Allotropes means chemical properties are same, but the physical forms are different. Such compounds are called as allotropes. So I am coming to the group 16 allotropes, group 17 allotropes. Group 16 elements exhibit allotropy, means they show allotropic properties. Oxygen having the two allotropes, O2 and O3. These are the allotropes of oxygen, O2 and O3. You know, O3 is ozone. Then sulfur exists in number of allotropic forms, but the monoclinic sulfur, rhombic is also called as alpha sulfur, and monoclinic sulfur is called as beta sulfur. These are the important allotropes of sulfur. Then selenium exists in two allotropic forms. The first one is red, it is non-metallic, and gray is metallic. Then tellurium, it is also exists in two allotropic forms. First one is crystalline, and second one is amorphous. Polonium also exists in two allotropic forms. One is alpha and another one is beta. Both are metallic. So question is asked for the board examination for 1 mark. Explain the allotropes, different allotropes of group 16 elements. So if it is asked for 2 marks, only we have to write the allotropes. Oxygen have 2 allotropes, then sulfur exists in many allotropic forms. 2 marks question will be asked. No, if the 1 mark question will be asked, they will specific, they will give the name of the element. Write the allotropes of selenium, for example, write the allotropes of tellurium, write the allotropes of polonium. So these questions will be asked for 1 mark. And if the term allotropy is asked for the examination, it will be asked for 2 marks, remember. So oxygen allotropes are O2, O3, sulfur having the many allotropic forms, but rhombic, it is also called as alpha, and monoclinic is beta. We will discuss the details of this monoclinic and rhombic sulfur. Then selenium exists in two allotropic forms, red, metallic, gray, sorry, red non-metallic, gray is metallic. Then tellurium exists in two allotropic forms, crystalline, amorphous, and polonium is alpha and beta. So we will discuss this allotropes of sulfur. So as explained in this earlier explanation, sulfur exists in many allotropic forms, but these rhombic sulfur, it is called as alpha, and beta sulfur. We will discuss in this tabular format. It is given in detail. We will discuss. So this is a rhombic. In this side, rhombic sulfur, it is alpha, and this is beta sulfur. For the differentiation also, it can be asked for the exam. Differentiate between rhombic sulfur and monoclinic sulfur. So color of this alpha sulfur is a pale yellow color, and color of this monoclinic sulfur is a bright yellow solid, remember. So the color is also different. The shape is orthorhombic. Alpha is orthorhombic and beta is needle shaped. It is a monoclinic crystals, the melting point is given 385.8 Kelvin, and the melting point of this monoclinic sulfur is or beta sulfur is 393 Kelvin. The density is a 2.063 per cm cube. This is having more density, and the density of this monoclinic sulfur is quite less, 1.98 per cm cube. Solubility, these are insoluble in water. Rhombic sulfur is insoluble in water but soluble in carbon disulfide. This monoclinic sulfur is soluble in only carbon disulfide. Then saying stable below 369 Kelvin. This rhombic sulfur is stable below 369 Kelvin, and it is converted into beta sulfur above this temperature, remember. So if the temperature is more than 369, this alpha sulfur, it is converted into beta sulfur. They are stable above 369 Kelvin, and they are converted into alpha sulfur below this temperature. So this is the stability. Then structure, this rhombic sulfur exists in S8 molecules having puckered ring structure. I will show the structure of this rhombic sulfur also. Then monoclinic sulfur, S8 molecules with puckered ring structure, both having the same structure. Method of preparation, it is prepared by the evaporation of roll sulfur in carbon disulfide. Then rhombic sulfur is melted in a dish and cooled till the crust is formed. Then the two holes are made in the crust and remaining liquid is poured out, give the needle shape. So this method of preparation is asked, it is not asked for the board examination, remember. So any 4 points we have to remember out of this: color, shape, melting point, density, solubility. The question can be asked for the 2 marks, a difference between rhombic sulfur or difference between monoclinic sulfur. Or they will ask the question like this: write a note on rhombic sulfur for 2 marks. So we have to write the color, shape, melting point, density, stability, then structure, draw the structure for 1 mark. So I will show the structure of this rhombic sulfur. See, this is the structure of this rhombic sulfur. It is puckered ring structure. 1, 2, 3, 4, 5, 6, 7, 8. So this is a S8 molecule. S8 molecule having, this is a bond length. Sulfur bond length is 2.04 picometer, and the angle between source sulfur is 107 degrees. We can see clearly the angle, and this is a bond length sulfur. This is sulfur bond length. All the sulfurs having the same bond length is 2.04 picometer. So this is the structure of S8 ring in rhombic sulfur. It is a puckered ring structure, crown shaped structure. This is a chair form of S6. As I explained earlier, sulfur exists in many allotropic forms. So this is a S6 chair. It is like, say, 1, 2, 3, 4, 5, 6. See, the bond length is also different. It is 205.7. Sorry, it is a picometer to sorry, this is angle is given. Some spelling mistake is there. Yes, the angle is given here, 205.7 degrees Celsius. This is the angle, and this angle is different. This angle is different, and this angle is different. This is a 202.2 degrees. 2 is remaining here, 202.2 degrees Celsius. So this is for extra knowledge. This is not asked for the examination, remember. Because whatever the part given in the boxes, it will be not asked for the examination. This will be asked for the CET examination, remember. This remember part, it is not asked for the examination, board examination. it will be asked for the competitive examination. So this part is given for the extra knowledge, but this question can be asked for the examination. I am going to read the question. Which form of sulfur shows paramagnetic behavior? Paramagnetic means unpaired electron should be there. So in vapor state, sulfur partly exists as S2 molecule. S2 molecule which is having the two unpaired electrons in the antibonding antibonding molecular orbital. Pi star, this is antibonding molecular orbital. Like oxygen, S2 molecule and O2 molecules are behave same. So as O2 molecule is paramagnetic, this S2 molecule is also paramagnetic in nature. So this question can be asked for 1 mark or 2 mark. This is a 2 marks question. Why? Which form of sulfur exists in paramagnetic nature? So the answer is S2 molecule, because S2 molecule in vapor state, it behaves as oxygen molecule. So oxygen also having the antibonding orbital, unpaired electrons are there, two unpaired electrons are there. So S2 molecule also having the two unpaired electrons. So if the two unpaired electrons is there, it is paramagnetic, and if there is no any unpaired electron, it will be diamagnetic in nature. So remember this difference between rhombic sulfur and monoclinic sulfur. The stability, once again I am explaining the stability. So the stability, rhombic sulfurs are stable below 369 Kelvin, remember. Means at the temperature 369, both are stable. This is stable below 369 Kelvin and transferred to beta sulfur above this. Means if the temperature is 370, the rhombic sulfur will be converted into monoclinic sulfur. This is stable above 369, means if the temperature is below than this 369, it will be converted into alpha sulfur. Meant at the temperature 369, both the allotropic forms are stable. So such type of question can be asked for the examination. Mention the temperature at which both the allotropes of sulfur, means both the allotropes, rhombic sulfur and monoclinic sulfurs, are stable. So such questions are also asked for the CET, and students neglect this difference. So don't neglect the difference. Many questions can be prepared from this table. What is the shape of monoclinic sulfur? What is the shape of rhombic sulfur? It is the shape is orthorhombic crystals. It is a needle shaped. Also, it can be puckered ring structure. This is a acid molecules with puckered ring structure, both having the puckered ring structure, but the shape is different. It is a orthorhombic crystal, and this is a needle shaped crystal. Monoclinic are always needle shaped. Then they can ask the density also. What is the density of rhombic sulfur? What is the, but numbers cannot be asked for the examination. Remember, the numbers they will not ask for the exam. Melting point will be not asked, density will be not asked, but they can ask the color also, they can ask the shape also. So don't remember the numbers, melting point, boiling point, then temperature, it will be not asked for the examination. It is not expected from the student. Now the next part is oxo acids of sulfur. So these structures are asked for the examination, remember. Draw the structures of oxo acids of sulfur and oxo acids of chlorine are given here. In the next slide, oxo acids of chlorine are here. First, I will explain. This is oxo acids of sulfur. There are 1, 2, 3, 4, 5, 6 structures are given. First one, we will discuss this sulfurous acid. Sulfurous acid is different than the sulfuric acid. Is H2SO3. H2SO3, see the structure, sulfur is at the center, H2, 1, 2, H2 is completed, and this is the sulfur S, and these are the 3 oxygen. Single oxygen is a double bonded, and this is OH, OH. So this is H2SO3. Make a practice at your home, draw the structure. So structures are asked for the 2 marks, 3 marks, or 4 marks. Many times these structures are asked for the 3 marks also, 4 marks also. They can ask the question, draw the structure of sulfurous acid. They will give the name only. We have to remember the formula. They will not give the formula. They will give the name only. Draw the structure of sulfurous acid. So we have to remember the name. H2SO3 is sulfurous acid and H2SO4 is sulfuric acid. See the difference between these sulfurous and sulfuric acid is one oxygen is extra. See OH, OH, and this structure is same. OH, OH and double bonded oxygen is the structure is same. Instead of this lone pair, another oxygen is there. So this is the structure of sulfuric acid. We have to make a practice of these structures, then we will remember. Then I am coming to the next one. It is called as a disulfuric acid, or it is also called as pyrosulfuric acid. H2S2, where sulfurs are 2, H2S2O7. So this is first we will coming to this H2. This one H, another H is H2 is completed. Then S2, two sulfurs are there. Here is number 1, number 2, H2, S2, and 7 oxygens are there. 1, 2, 3, 4, 5, 6, 7. So these are the 2. 2 plus 2, these are the 4. See 1, 2, 3, 4, 5. H2S2O7. 1, 2, 3, 4, 5, 6, 7, 8. One mistake is there in the structure. This is wrongly drawn. I will make a correction in the structure because there are 8 oxygens. 1, 2, 3, 4, 5, 6, 7, 8. So this is a wrong structure. I think O8 H2S2O7. I will show the structure. See, in this diagram, I will show the structures. So this is a sulfuric acid, H2S2O8. We have to discuss the structure of. See, H2S2O8. This is a peroxysulfuric acid. H2S2O7. We are discussing about the H2S2O7. This is a, yes, this structure. Pyrosulfuric acid. So this is a pyrosulfuric acid H2S2O7. This is also called as oleum. Oleum. See this number of oxygens. 1, 2. This is 1, 2, 3, 4, 5, 6, 7. So this structure is a pyrosulfuric acid. In your textbook, there is a mistake of this structure. Instead of this structure, Another structure is written here, so make a correction. I will send the correction. I will make the correction in the PPT and I will send again. So again, I am coming to this structures of next one. Yes, this H2S2O7 is wrongly written. Then I am coming to this H2SO5. H2SO5 is a peroxy monosulfuric acid. Calculate the number of oxygens again. Peroxy monosulfuric acid H2SO5. So there is a first hydrogen, two hydrogens are completed, then sulfur is there, and SO5, 1, 2, 3, 4, 5. So this is correct. H2SO5 is called as peroxy monosulfuric acid. Then this is a peroxy disulfuric acid, H2S2O8. This is a wrongly written. Instead of this H2H2O7, this H2H2O8 is there. So this structure should be drawn here and this should be drawn here. So there is a mistake in these two structure, peroxy disulfuric acid and this is a pyrosulfuric acid. Actually this is the structure of peroxy disulfuric acid and this is the structure of pyrosulfuric acid, because there are 7 oxygens are there. 1, 2, 3, 4. 1, 2, 3, 4, 5. Again, it is wrongly written. So all these structures I will send again, because I want to check this structure. Some mistake is there. We will discuss the structures of oxoacids of chlorine. So there are 4 oxoacids of chlorine, remember. First one is hypochlorous acid, HOCl. HOCl is hypochlorous, then HOClO2, or it is also called as HOClO. Only oxygens we are increasing. See, hypochlorous is 1 oxygen, then is chlorous 2 oxygen, then 3 oxygens and 4 oxygens. The names will be also changed. It is hypochlorous, then chlorous, chloric and perchloric. And only 1 oxygen we are going to increase. It is HOCl, it is HOClO2, or it is also written as HClO2. Sorry, HClO2, here HOCl, there HClO3, and this is HClO4. So the oxygens are increasing. Hypochlorous, HOCl. See the structure, HOCl, and here another oxygen is increased, HOClO. It is also called as HClO2, and another 1 oxygen is increased and another oxygen increase. So structures are very easy. Only we have to increase the oxygens here. These structures can be also asked for the examination for 1 mark or 2 mark. Draw the structure of hypochlorous acid, draw the structure of chlorous acid, draw the structure of chloric acid, and draw the structure of perchloric acid. So these are the oxoacids of halogens. Some oxoacids are given in this table, oxoacids of halogen. See the oxidation state, and then the name is given here. The oxoacids of fluorine, oxoacids of chlorine, oxoacids of bromine, and oxoacids of iodines are given. So from this table we can clearly see only chlorine shows all the acids. This is a hypochlorous. See, the hypohalous means it is hypochlorous. This is a chlorous. This is a chloric, and this is a perchloric acid. So oxidation state, it is a +1, it is a +3, it is having the +5, and it is having the +7 oxidation state. So only the oxoacids of chlorine, these are the stable. These oxoacids of fluorine, there is only 1 oxoacids of fluorine is only hypochlorous acid. This is HOF is hypochlorous. This is hypobromous. This is hypoiodous acid. Oxoacids of bromine, there are only 1, 2, 3 HOBRO2. This is a bromic, and this is a perbromic. This is a iodic acid, and this is periodic acid. The general formula is given here: hypohalous acid, halous, halic, and perhalic. So acid strength increases from HOCl to HClO4. So this is a weak acid. HOCl is a weak acid, and this is a strong acid. So the structures are asked for the examination. Remember, on this topic, the main important point is structures are asked for the examination. So today again I will send these structures, corrected structures, because there are printing typing mistake, or the structures are wrongly drawn in this slide. So again I will send these structures. Then the next part is compounds of sulfur. And I want to remind one thing: oxygen and compounds of oxygen, this part is deleted. So I request open your textbook. In the textbook, page number 148, oxygen and compounds of oxygen, it is deleted. That is page number 148 is deleted. Page number 149 is deleted. Page number 150 is deleted. Page number 151 is deleted. Directly come to the compounds of sulfur, that is page number 152. So the deleted part is not taken in these notes. Remember, deleted part is also deleted from this PPT also. The next part is compounds of sulfur. First one is sulfur dioxide, it is SO2. So first one is preparation of this sulfur dioxide, it is SO2. Sulfur dioxide is prepared from sulfur. Yes, by burning of sulfur in air. So sulfur dioxide is also, it is present in gaseous state. It is prepared by burning of sulfur in air. So sulfur, it is in solid state. Oxygen means it is burned in air. We directly get SO2 gaseous. So it is a preparation of sulfur dioxide by using sulfur. Then next one, in laboratory, it is prepared by using sulfite. So it is prepared by using sodium sulfite. This is Na2SO3. It is sodium sulfite. It is treated with dilute H2SO4 sulfuric acid. We get here H2O plus SO2 plus Na2SO4. Sodium sulfate plus water plus sulfur dioxide. Gas is liberated. So this is a laboratory method of preparation of sulfur. Then from sulfides, it is in industrial method. When large amount of sulfur dioxide we have to prepare, we are preparing from this sulfides. So the reaction is given with zinc sulfide. Sulfur dioxide can be prepared by roasting zinc sulfide and iron pyrites. Roasting means in presence of air, roasting, and calcination. These are the two different processes used in metallurgy. So roasting means it presence of air, it is heated. So zinc sulfide plus 3O2, it is heated. We get air zinc oxide plus twice SO2. This is sulfur dioxide. And this is iron pyrites. This is a formula of iron pyrites. It is also heated in presence of air. We get twice FeO3, and make a practice at your home these reactions. So I